Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 1.4, Average Rate of Change and Instantaneous Rate of Change, or AROC and IROC for short. Let's explore this idea of average rate of change and instantaneous rate of change through this problem up here. Let's see what it says. Suppose a particle travels on the y-axis, so it's going to go up and down, such that its position, s, in meters, is a function of time in seconds. And we're going to model that function like this. S of t is equal to negative t squared plus 2t, where we plug in a t value for time, and it outputs a height in meters. Here's a table of values with various t values between 0 and 1 chosen. And if you want to verify, you could plug in those t values to our function. And you can see that our heights, our s of t's, will be what's given below, those values between 0 and 1 as well. Now, it's important to note and remember that this function, the time, is defined in seconds, and the s of t values are defined in meters. And our job is to find the average rate of change on a given interval from A to B. There's 4 different problems that we're going to do, but before we do them, what is even average rate of change? What does it mean? Well, for us, the easiest way to define average rate of change, or AROC, it's just the old school slope that you've learned since 6th, 7th grade. Right? You might remember the formula as the slope is equal to y2 minus y1 over x2 minus x1. The change in the y's over the change in the x's. For our purposes, and in calculus, we might use function notation a little bit more. So for us, and in particular this function, if we call our two values a and b, then our denominator will be b minus a, and our numerator will be the output values, s of b minus s of a. Same formula, a slightly different notational. With that in mind, let's find our average rates of change. Now would be a good time to pause the video to see if you can calculate these on your own. Welcome back. If we go over to our problem from 0 to 1, and we just plug in the values, s of 1 minus s of 0 minus over 1 minus 0, you can calculate that to be a value of 1. We do it for b, c, and d. Nothing surprising is going to happen. You can check those values there. If we calculate this slope or average rate of change on the interval 0.5 to 1, you should get 0.5. If we calculate the slope or average rate of change on the interval 0.9 to 1, plugging in the appropriate values, 1 minus 0.99 divided by 1 minus 0.9. Calculate it on your own, verify, but we should get an average rate of change of 0.1. And finally, doing it one more time, this is very tedious, but you've been finding slopes forever, so not hard. The slope on this interval should be, if we evaluate this rate of change, looks like it's going to be 0.01. Now, keep in mind that all of these have units, meters and seconds, and we're finding their rates of change. So they all should be in meters per second, which should make sense because we're finding how fast this particle is moving on average over these time intervals. And if you take a look at the progression of these rates of change, as our interval gets closer and closer to 1, 0 to 1, 0.5 to 1, 0.9 to 1, 0.99 to 1, you can see our rates of change are decreasing, which brings us to the final question of the day. What is instantaneous rate of change? Well, for me, instantaneous rate of change, or IROC, it's really where two worlds collide. I like to call it the calculus slope, but the two worlds that are colliding are our old school slope, right, what we've known and done forever, with the idea of limits, which is what we're building up and working with right now. We put those two together, that's what creates the instantaneous rate of change. So for our problem, we found all these slopes or average rates of change, And if we think about finding the limit of these average rates of change, we could estimate our IROC of S of t at t equals 1. Now take a look at our average rates of change, 1, 0.5, 0.1, 0.01. So these are all going down and going down, but they're slowing down as we get closer and closer to 0. So we might estimate that our instantaneous rate of change is 0. In other words, saying at t equals 1, we believe our particle has a rate of change of 0 meters per second. So it's not moving. To see more videos like this, click subscribe. Or to continue your journey through calculus, click the next video on your left.